So in that last section, we talked about one of the important things of NMR called nuclear spin. We discovered that the nucleus contains protons, the protons spin, and in the presence of a magnetic field, we get an unequal distribution of protons with a slightly few more being in the lower energy level than in the higher energy level. So let's look a little bit closer at this idea of the absorption of energy. So the nucleus begins to precess. That just means wobble. It's like a spinning top. When you spin it, it's moving around pretty tightly until it starts to slow and it starts to give a little bit of a wobble. With some angular momentum, right? It's angular momentum when a magnetic field is applied. Sometimes in NMR we call that the Larmor frequency. So the nucleus itself is charged, right? It has protons inside of it. So a moving charge, right, generates an oscillating electric field. There's a magnetic component with that too, of that same frequency. So if it's wobbling around at a certain frequency, then it generates this electric field at that same frequency. Right? So the idea there is magnetic field applied, nucleus begins to wobble a little bit, and it wobbles at a certain frequency. Now if we supply radio frequencies, right, remember nuclear magnetic remember nuclear magnetic resonance. Nucleus, right? It's the nuclear part. Magnetic field, resonance is going to require radio frequencies of that same wavelength are supplied to the precessing, that's just the wobbling, right? Nucleus. Energy can be absorbed in a process called resonance. So this is a big thing here, all right? So let's take a look at this down below and see if we can make sense of this a little bit more. All right, so just first things first, a naked proton, that's a 1H atom. So in other words, it's just by itself. It's not connected to another H atom. It's not connected to carbon. It's just by itself. With a B internal magnetic field, so if there's an internal magnetic field of 14,100 Gauss, then that nucleus precesses at 60 megahertz. Right? So then if we have an outside magnetic field of 14,100 Gauss, with a radio frequency of 60 megahertz, light comes in, right, comes over, and it hits the nucleus, that's our nucleus, and inside that proton feels 14,100 Gauss. So they equal each other, right? 60 megahertz, 14,100, same thing down below, inside the nucleus. And when that happens, the two frequencies couple outside and inside. The proton undergoes resonance and moves up to a higher energy level. Now, as that proton goes back down, it emits some energy. And that energy is what we're going to see plotted on an NMR. Okay? So I want to show you guys a little video here. Let's take a look. So here we have magnetic field applied, lower, higher energy level. Absorption, so same frequency coming in. Now we have a peak being shown here. Okay. Now, if this was the case all the time, then all protons would just always show up at the same exact place all the time, which is not very useful. It turns out that we almost never have just a naked proton. Protons are in chemical environments. Right, they're around other atoms like carbon and oxygen and nitrogen and sulfur and all double bonds and triple bonds, and those are different environments. So since the nuclei are surrounded by a cloud of electrons, those electrons can block out some of the external magnetic field in a process that's important to understand called shielding. So you're literally being shielded from the external magnetic field. So let's look at this a little bit in detail down below. Let's see what this has to say if we look at this first kind of scenario. So here we have a naked proton, Right, just a single H atom. External magnetic field outside, B outside, 14,100 Gauss. Well, it's naked, and we saw before that at 14,100 Gauss inside that we process at 60 megahertz. We're 60 megahertz right here. So that comes in, and then here we have absorption occurring. So we see that we'll be NMR active in this situation. So there's resonance occurs. So this one looks good. Right now, in a magnetic field that now let's look at the next one. So what we're going to have on this next one is now this kind of nucleus around us, okay? And in that nucleus, let's imagine that we have, or surrounding the nucleus, let's imagine that we have electrons. So that's an electron cloud here. It doesn't matter how many there are. Electrons move, and when they move, they generate a magnetic field. And that magnetic field can either add to the external magnetic field or subtract away from it. So in this shielding case, what we're going to imagine is that you have an external magnetic field outside of 14,100 Gauss. And as that energy comes in and passes through that electron cloud, we subtract out 10 Gauss. That's just a number I'm picking out of a hat, basically, right? So 10 Gauss here. So that means that inside that nucleus, you actually only experience outside magnetic field of 14,090. In other words, it says B inside, but that's what you feel inside because you've subtracted off 10 Gauss here. So if you want that proton to process here, down here, and flip up to a higher energy state, then you need to crank this thing up to compensate for the loss of 10 Gauss. So we're going to crank it up to 14,110. And that way, as that light comes through, that RF frequency comes through, we come down here, and we lose 10 from this, but now we have 14,100, and at 14,100, we have resonance occurring. So we see a peak show up on our NMR spectrum.